In this lesson, we are going to look at DHCP version 6. But before we start with the configurations and concepts of DHCP version 6, I think it would be good for us to have an overview of SLAAC. Before we begin that, let's look at an IPv6 GUA assignment. On a router, an IPv6 Global Unicast Address, or GUA, is manually configured using the IPv6 address followed by the IPv6 address and the prefix length for the interface. A Windows host can also be manually configured with an IPv6 GUA address configuration, as shown in the figure here. But then again, manually entering this can be very time-consuming because it has a lot of numbers, and also because it has a lot of numbers, it could be somewhat error-prone. Therefore, most Windows hosts are enabled to dynamically acquire an IPv6 GUA configuration. If automatic IPv6 addressing is selected, the host will use an ICMPv6 router advertisement message, or RA. This message is to help it auto-configure an IPv6 configuration. The IPv6 link local address is automatically created by the host when it boots and the Ethernet interface is active. The interface did not create an IPv6 GUA in the output because the network segment did not have a router to provide network configuration instructions for the host. So the first thing it has is just the link local address, like this. By default, an IPv6 enable router periodically sends the ICMPv6 router advertisements, which simplifies how a host can dynamically create or acquire its IPv6 configuration. A host can dynamically be assigned a GUA using stateless or stateful services. All the stateless and stateful methods in this module uses the ICMPv6 router advertisement messages to suggest to the host how to create or acquire its IPv6 configuration. Although host operating systems follow the suggestions of the RA, the actual decision is ultimately up to the host. So if we look at the figure, you'll find that dynamic GUA assignment can be divided into stateless or stateful. Now, stateless means it doesn't track any state, so there is no device tracking the assignment of the IPv6 address. In stateful, a DHCP version 6 server is managing the assignment of the IPv6 addresses. Under the stateless, we have SLAAC only, and we have SLAAC with DHCP server, or also known as stateless DHCP version 6. Under stateful, we have the stateful DHCP version 6. In SLAAC only, the router sends a router advertisement message providing all IPv6 addressing information, which include network prefix, prefix length, and default gateway information. Hosts use the RA information exclusively for all their addressing, including creating their own GUA. So in this instance, there is no DHCP server. In the stateless DHCP version 6, the router RA messages provide the IPv6 configuration information to host and then inform the host that they have to contact the stateless DHCP server for additional configuration information. So hosts use the RA information to create their own unique GUA and get the additional information from a DHCP version 6 server. So in this case, a host gets part of its information from the router advertisement, and then it gets the rest of the information from the DHCP server. In the stateful DHCP version 6 server, router advertisement messages inform hosts to contact the stateful DHCP server or DHCP version 6 enabled router for all IPv6 configuration information except for the default gateway address. So hosts will contact the DHCP server to acquire all of their IPv6 addressing information, and host obtains default gateway information from the router RA messages. These are three different ways a host can get a dynamic GUA assignment. So how does a router know which one of the three is going on or is in play. So how a client obtains an IPv6 GUA depends on the settings in the RA message. In the RA message, there are three flags: the A flag, the O flag, and the M flag. The A flag is the address auto-configuration flag. This flag signifies that it's using the stateless address auto-configuration or SLAAC to create an IPv6 GUA. The O flag is the other configuration flag, and it signifies that additional information is available from a stateless DHCP server. The M flag is the Manage Address Configuration flag, and it signifies to use a stateful DHCP server to obtain an IPv6 GUA. This is what the router uses to signify whether they are using SLAAC only, a stateless DHCP, or a stateful DHCP version 6. Using different combinations of the A, O, and M flags, RA messages inform the host about the dynamic options available. So for example here, when a host enters the network, it would send a request or solicitation. Okay, it would say, I need an RA from R1. So then the RA from R1 could be these options. If the RA is this, A flag is 1, O flag is 0, M flag is 0, that means only use this information to set up your GUA. If the RA says A flag 1, O flag 1, and M flag 0, this means that you get the basic information from the RA, but for additional information, you have to go to the DHCP server. If the flag A is set to 0 and M is set to 1, that means it is stateful DHCP version 6. You have to get all your information except the default gateway from the DHCP server. So let us look at SLAAC for a little bit. Not every network has access to a DHCP server, but every device in an IPv6 network needs a global unicast address. The SLAAC method enables hosts to create their own unique IPv6 global unicast address without the services of a DHCP server. SLAAC is a stateless service, which means there is no server that maintains network address information to know which addresses are being used and which ones are available. SLAAC sends periodic RA messages about every 200 seconds, providing addressing and other configuration information for hosts to auto-configure their IPv6 address based on the information in the RA. A host can also send a router solicitation or RS message requesting an RA. This is usually done by a host that has newly entered the network. SLAAC can be deployed as SLAAC only or SLAAC with DHCP version 6 or stateless DHCP version 6. In the topology, we could see that we have PC1 that is attached to R1, and R1 interface G001 has been configured with the IPv6 GUA and the link local address. The R1 G001 interface IPv6 addresses include the link local IPv6 address, the GUA and the subnet, and the IPv6 all nodes group, which is FF02:1. So we have the link local address, the GUA, and then the subnet, and also the group. R1 is configured to join the all IPv6 multicast group and start sending RA messages containing address configuration information to hosts using SLAAC. The IPv6 all routers group responds to the IPv6 multicast address of FF02:2. Here, we see that the command show IPv6 on the interface and the section join, it shows that this particular group, the IPv6 all routers group, is there. R1 will now begin to send RA messages every 200 seconds to the IPv6 all nodes multicast address FF02:1. R1. Now let's look at the SLAAC only method, meaning that the host will get all its information to create its own GUA from the RA only. So RA messages from R1 have the following flag set. Flag A is set to 1. It informs the client to use the IPv6 GUA prefix in the RA and dynamically create their own ID. The flags O and M are set to 0, and this informs the client that there is no other server for additional information. All the information you need is in the RA. The ipconfig Windows command confirms that PC1 has generated an IPv6 GUA using the R1 RA, or the router advertisement messages from R1. The default gateway address is the link local address of R1 G001 interface. So once PC1 enters the network, then R1 would send an RA to PC1, and that RA would have the flag A set to 1 and all the other flags set to 0. This basically tells PC1, I'm giving you some information, use this information to create your own IP address. So PC1 will then create his own IP address, and now we have the IPv6 address for PC1. It has the link local address, and then it has the default gateway, which is the link local address of this interface in R1. A router sends router advertisement messages every 200 seconds, or when it receives a router solicitation message from a host. IPv6 enabled hosts wishing to obtain addressing information send a router solicitation message to the IPv6 all routers multicast address FF02::2. So let's look at this figure. This figure illustrates how a host initiates the SLAAC method. Firstly, the PC has just booted and sends a router solicitation message to IPv6 all routers multicast address, and then is requesting an RA. R1 generates an RA and then sends the RA message to the IPv6 all nodes multicast address, and then PC1 uses this information to create a unique IPv6 global unicast address. Using SLAAC, a host acquires its 64-bit IPv6 subnet information from the router RA and must generate the remainder 64-bit interface ID using either randomly generated or EUI64. In randomly generated, the 64-bit interface ID is randomly generated by the client operating system. This is the method now used by Windows 10 hosts. EUI64, on the other hand, the host creates an interface ID using its 48-bit MAC address and inserting the hex value of FFFE in the middle of the address. Some operating systems default to the randomly generated interface ID instead of the EUI64 method due to the privacy concerns. This is because the Ethernet MAC address of the host is used by EUI64 to create the interface ID. Now, if the hosts are all generating their own ID, is there a possibility that two hosts creating the same ID? A SLAAC host may use the following duplicate address detection or DAD process to ensure that the IPv6 GUA is unique. The host sends an ICMPv6 neighbor solicitation message with a specially constructed solicited node multicast address containing the last 24 bits of IPv6 address of the host. If no other devices respond with the neighbor advertisement message, then the address is virtually guaranteed to be unique and can be used by the host. If an NA is received by the host, then the address is not unique, and the host must generate a new interface ID to use. One thing to note though, that is really not required because a 64-bit interface ID provides 18 quintillion possibilities. Therefore, the chance of a duplicate address is remote. However, the IETF recommends that DAD is used. Therefore, most operating systems perform DAD on all IPv6 unicast addresses regardless of how the address is configured. That is the end of the overview of SLAAC. In the next lesson, we will look at how DHCP version 6 is done. Until the next lesson, goodbye.